We're putting together a simple optical system in order to produce a parallel beam of light. There's a circular aperture in this light shield. George is placing a carbon arc behind it. The arc approximates a point source of light. The fluorescent solution in this glass tank shows a divergent beam. But, as I've told you, we want a parallel beam. George is introducing a collimating lens. A second lens focuses the light on a little screen. It's the image of the brightly lit circular hole in the light shield. The beam between here and here is still parallel. This is a red filter. It passes only a narrow band of red wavelengths. The red image on the screen is, of course, far less intense. Between these 2 points, the beam is monochromatic. I'm putting a glass prism into the beam. The red spot disappears because it has been refracted by the prism. It is bent away through quite a large angle. We are now looking at a trace of the beam from above. The light beam is refracted as it enters glass. It is bent toward the line which is normal to the glass surface. We hope that you have heard before of Snell's law, which governs this phenomenon, and how this law can be derived from 2 important assumptions. These are, first, that light is a wave motion, and second, that its speed is less inside the glass than outside. In this film, we are not concerned with the simple derivation of the law of refraction. Rather, we ask the question, why is the speed of light less in glass than outside? Why does the glass prism slow red light down? As we look for an answer to this, we'll continue to assume that light is a wave. To be precise, an electromagnetic wave. So, I want you to think of a single monochromatic light beam, a sinusoidal wave of given frequency. By its speed, I mean the speed with which its phase advances. This is the so-called phase velocity. In free space, it has the value 3 times 10 to the 8 meters per second, and it's usually denoted by the letter c. The speed of light in free space is the same for all frequencies. This isn't true, you know, when light passes through matter. The phase velocity of light in a given material can be different for different frequencies, and what's more, it can even be larger than c for some frequencies. All this is possible because of the way the atoms and molecules of the material react to the light as it passes over them. So, to begin our classical theory of refraction, let us think first of empty space. Then, of a light wave coming at us through the empty space with speed c. We plan to fill the outlined part of space with a material, such as glass or another dielectric. We shall think of it in successive molecular layers and have indicated the first layer. Let's concentrate on this layer. The incident electromagnetic field oscillates as the light wave passes over the layer. The vertical oscillating vector is the electric field. It causes the electric charges in the molecules to oscillate up and down, the positive charges one way, the negative charges oppositely. The 2 kinds of charge are separated. The electric field creates oscillating molecular dipole moments. Now, the magnetic field, which oscillates horizontally here, also exerts a force on the moving charges in the molecules. But this force is small because the speed v of the moving charges is very small compared to c. We can neglect its effect in our discussions. Notice that we chose to let the molecular dipoles oscillate in phase with the incident wave. We don't really know why they should be in phase. At this point, let's just assume that the molecular oscillators respond in phase. We'll prove to you that this leads to a slowing down of the light, which will explain the bending of red light toward the normal as it enters glass. What is important to us now is to realize that the oscillating dipoles will radiate. Each will send out its own little electromagnetic dipole wave, which will spread from it in all directions. We want to know their effect at forward points. Any point, such as the one marked P, will receive a small signal from each of these dipoles. In addition, of course, the incident wave will get through to P. For instance, consider the wave from the dipole at top right. A signal will go from it towards point P, also with speed c. But this dipole is an outlying dipole. It is further from P than the dipole on the axis, indicated here. The signal takes longer to reach P from the outlying dipoles than from those near the axis. So, the signal arriving at P from an outlying dipole at any given instant will lag in phase behind the signal reaching P from the dipole on the axis at the same instant. It will also lag the phase of the incident wave reaching P. One can calculate the resultant phase delay in the composite wave from all the dipoles. Perhaps surprisingly, this phase delay turns out to be exactly 90 degrees. The composite dipole wave reaches point P 90 degrees behind in phase compared to the incident wave. This happens to be true for any forward point, not just the one we originally chose. The phase lag will be 90 degrees even if P lies in the next layer. So the two signals go on to the next layer, the incident one undelayed in phase, and the compound one from all these dipoles, which lags the first by 90 degrees. Clearly, the superposition of these two signals will have a phase delay, though less than 90 degrees. So, the total signal is delayed compared to what would be the case if there were no molecules there. The resultant light wave is delayed by the first layer. In turn, the next layer will delay the light wave, and so on. Its phase proceeds more slowly than through vacuum. The speed of the phase is less than c. And light beams, which are obliquely incident on the dielectric, are bent toward the normal, as we saw before. The explanation we have given is oversimplified. It is based on the forward radiation of a single layer. Actually, each dipole layer also radiates backwards. The backscattered dipole waves from interior layers, such as this one, are scattered forward again, and so on. An exact theory must take such multiple scattering into account. It turns out, however, that our simplified explanation reaches the same qualitative conclusions as does the exact theory. To summarize, we've been treating the incident light as an electromagnetic wave. Its effect on the molecules of the optically transmitting materials is to convert them into oscillating dipoles. Since these materials are non-conductors, the oscillating electric charges in their molecules will remain bound to each other. When you stretch the bound charged particles away from their equilibrium positions, they will experience a restoring force pulling them back together toward equilibrium. Let us make another bold assumption, namely, that the restoring force is linear, which means it is proportional to the amount of displacement, as, for example, in a mass connected to a spring. This system can oscillate on its own with a natural frequency. It is weakly damped, mostly by the wheel bearing. Similarly, the oscillating dipoles experience damping. But here, a good part of the energy they lose will go off as radiation. An eccentric linkage creates an oscillating force. It drives the outer end of the coil spring. The other end is attached to the wheel's axle. Keep your eye on the 2 pointers. One is attached to the driving bar and the other to the wheel. They allow us to compare the response of the wheel to the driving force. The frequency is small and lies far below the natural frequency of this oscillator. Notice that the wheel follows at the same frequency. And if it weren't for static friction temporarily freezing the bearings of the wheel at the amplitude position, the wheel would follow the driver exactly in phase as well. Similarly, our molecular oscillating dipoles will follow exactly in phase if they are driven by incident light whose frequency lies sufficiently below their natural frequency. Static friction does not occur inside individual molecules. George is raising the driver frequency toward the natural frequency, but it is still below it. The wheel again follows at this new and larger frequency. Two things have changed. The amplitude has grown, and the wheel lags behind the phase of the driver. It can't keep up. This phase lag increases as the driver approaches the natural frequency. The driver frequency is now set to the natural frequency. The response amplitude grows quite large. We call this condition resonance. Notice that the oscillator is at its extreme, its amplitude position, just starting back, at the same time that the driver passes zero. The oscillator lags the driving force by 1/4 oscillation. At resonance, the phase lag is 90 degrees, and the amplitude has maximum value. The phase lag continues to increase as the driving frequency is raised beyond resonance. It reaches 180 degrees as a limiting value. Notice that the oscillator's amplitude is down again and that it lags the driver by half an oscillation. For example, the driver is at extreme right when the wheel is at extreme left. The phase lag is 180 degrees. Keep in mind these properties of harmonic oscillators regarding amplitude response and phase lag. They apply to the electric dipole oscillators driven by an electromagnetic wave. Of course, the dipole's resonant frequency is much higher than for our mechanical analog. It might lie anywhere in the electromagnetic spectrum. As a matter of fact, there may be many different resonances for any one material. We return to the molecular layer driven by an incident light wave. Remember that we chose the dipole response to be in phase with the oscillations of the incident field. We now understand the significance of this choice. The dipole oscillators have their own resonant frequency, but the frequency of the incident light is far below this resonance. Even so, the layer delays the resultant signal, as I explained earlier, because the radiation from the various dipoles of the layer has to cover large distances to reach a forward point, such as P. At frequencies below the dipole's resonance, the phase velocity of light in the material is smaller than c. Consider the oscillating electric field in a wave arriving at P. This vector can be defined as the projection of a uniformly rotating vector of fixed length called a phasor. It goes around once for each full oscillation of the field vector. Its length equals the field's amplitude. To make our construction simpler, we fade out the oscillating field vector. We just agree that the projection of this phasor upon a vertical line through the dot is the electric field arriving at P. Let's suppose that this phasor corresponds to the incident field, which has gotten through the molecular layer. Now, in addition, the dipoles in the layer radiate forward. And as we told you earlier, the composite wave from all the dipoles in the layer lags behind the incident wave by exactly 90 degrees. The superposition of the two waves is the projection on the red vertical line of the rotating resultant. Notice that the resultant lags behind the incident wave. Now that we know that these phasors are supposed to be rotating vectors, we can stop them and let this arrow remind us. So here we have our schematic representation of conditions at a point, P, beyond the dipole layer. The 90-degree phase delay in the radiation from the dipole layer causes the resultant signal to have this phase lag relative to the incident radiation reaching the point. Let me again remind you that this condition occurs when the dipoles in the layer respond in phase to the incident wave as it passes over the layer. This happens when the frequency of the incident radiation lies sufficiently far below the dipole's resonance. Next, let us figure out what should happen if we raise this frequency toward resonance. By our mechanical analogy, we know that as we do this, the dipole response becomes stronger and its phase begins to lag. At resonance, the lag reaches 90 degrees and the response amplitude is at maximum. So, the dipole radiation from the layer toward forward points such as P will acquire additional phase delay, and the phasor representing it will point downward in this picture. At resonance, it will point vertically down. Let's look at this again. As resonance is approached, the amplitude of the dipole wave grows toward a maximum. We shall repeat this motion a third time, and as you look at it, concentrate on the resultant. The phase lag of the resultant signal first increases, reaches a maximum, and then decreases. At resonance, the resultant is in phase with the incident component. At the same time, the resultant becomes shorter and shorter. By the way, we can now begin to draw a qualitative graph of the phase velocity of light in optical materials as a function of frequency. In vacuo, it has the same value for all frequencies. We call it C. But in an optical material, the dipoles resonate to some frequency, F0. If the light incident on it has a frequency quite a bit below F0, the resultant signal, which is represented by the white phasor, lags only a bit behind in phase. Compared to C, the phase velocity is reduced only a small amount by the material. But when we use light of higher frequency, the phase lag at first increases. The speed of light in the material falls further below C. When the material is glass, this is the frequency range for visible light. Glass refracts blue light more than red light. It has a resonance in the near ultraviolet. If a beam of white light falls obliquely on a glass surface, blue is bent more than red. As we increase frequency further toward the resonance value F0, the phase delay reaches a maximum and then it decreases. Correspondingly, the phase speed goes through a minimum. Finally, at resonance, the phase lag in the total disturbance is 0. The speed rises again, reaching C at resonance as if we had a vacuum. Notice also how small the white phasor is at resonance. Very little light gets through. In other words, near F0, the material absorbs the light. It is opaque there, or nearly so. If some of these conclusions are a surprise to you, wait, we are in for more surprises when we consider the conditions for light of even higher frequencies. As you remember, an oscillator will lag even more behind the driving force above resonance. So, for these higher frequencies, the dipole wave will lag behind even more than at f0. From resonance on upward, the dipole wave's phase delay increases from 180 to 270 degrees. Above resonance, the dipole oscillators respond with lower amplitude again, so the phasor representing the dipole wave would shorten as we think of larger and larger frequencies. The resultant signal grows in amplitude. The material is again transparent. But, even more importantly, notice that the resultant wave signal, which at the resonance f0 was in phase with the incident signal, now leads it. What was a phase lag below f0 now is a phase lead above. The phase of light moves faster than c through the medium. Phase velocity can exceed the speed of light in free space. Keep in mind that only the resultant wave's phase moves faster than c. The individual dipole waves, the incident wave, all these waves move from atom to atom through the intervening space at speed c. No signal actually moves faster than c. Our curve is called a dispersion curve. It tells the story about what happens to light in the neighborhood of a frequency where its medium has a resonant response. Below resonance, the phase of light moves more slowly than in vacuo, and a beam obliquely incident on the material will be bent toward the normal. Near resonance, the material is opaque. Above resonance, an obliquely incident beam should be bent away from the normal. Yes, that must be true, because we just saw that above resonance, the wave has a phase velocity which is larger than in vacuo. Still, you might be skeptical, so we'll check it by experiment. We need two things. First of all, we need a material whose atoms or molecules have a resonance in some range of wavelengths. Secondly, we have to make a prism out of this material. Now, let's suppose the material's resonance lies in the yellow region of the visible spectrum. The wavelengths of red light are longer than yellow. So the red frequencies lie below the resonance in the yellow. Red light will be refracted downward by the prism. The frequencies of light on the blue side of yellow lie above the resonance. Green light will be refracted upward by a prism whose material resonates in the yellow. Its phase velocity is larger than c in the material. So this is the effect we should look for. I plan to make our prism out of the hot vapor of sodium metal. Sodium vapor can be made to radiate strongly at a natural frequency in the yellow region of the spectrum. Let me show you. I'm cutting some small pieces of sodium. Let me put one on a little platform above this burner. When sufficiently heated, sodium vapor will glow bright yellow. Exactly the same radiation is produced in a sodium lamp by an electric discharge. In our next experiment, we'll take a look at the spectrum of the light from heated sodium vapor. For this purpose, I've set up a glass prism spectroscope over here. Our sodium lamp is the light source. And with the help of a condenser lens in here, it illuminates a vertical slit. The light from this slit is collimated by another lens, and just beyond it, I have a little platform on which I'll mount this prism. Actually, it's a series of 3 prisms. Together, they form a good dispersive element for visible light. But the dispersed light is sent generally forward, which a single prism would not do. A so-called direct view prism. It's quite convenient. I'll make a movie of the sodium spectrum with this camera. The light comes in narrow wavelength bands. We see slit images in different colors. The brightest spectral line is yellow. Here you see our spectroscope again, but this time the light source is a carbon arc. The spectrum of the white light from the arc is continuous. This shield has holes in it to permit light to pass through. Inside it is the sodium burner we used before. I'm putting it in the path of the white light from the arc. The occasional flickering you see, extending over the entire spectral range, is due to smoke from the flame throwing a shadow on the slit. As hot sodium vapor forms, it absorbs light in a narrow region of the yellow part of the spectrum. We may think of sodium atoms in the vapor as oscillating dipoles driven by white light. That means light waves of different frequencies. But sodium has a natural frequency in the yellow. So, there is a resonance in the yellow, and light is absorbed there. In sodium vapor, the resonance is very sharp and narrow. Now let's go on to the prism of sodium vapor. We'll produce it in this device. It's basically a steel tube. Glass windows have been sealed to each end with flanges. There already is some sodium metal in the tube. Through this access pipe, which has a valve in it, most of the air has been evacuated from the tube. At each side, a copper pipe is wound around the tube and soldered to it. A straight piece connects the coils along the top. Cold water is running through the copper pipes. A gas burner will heat the bottom from a line of flames. With the bottom hot, the top and sides cold, sodium vapor will be most dense near bottom center. It will be least dense along the top and at each end because the vapor will condense on the cold sections. Altogether, this density variation will form what is, in effect, a vapor prism oriented this way. It will refract red light down and green light up. I've put up a simple spectroscope for this prism. Our light source is a carbon arc. Light from the arc is focused on a slit. The slit is horizontal because it must be parallel to the refracting surfaces of the vapor prism, which are oriented this way. The vapor prism is only the first part of a double spectroscope. The second section involves the glass direct view prism, mounted as before. It disperses the light rays from the carbon arc in a horizontal plane, red going there, green and blue this way. The second slit is vertical. It's perpendicular to the first slit. Let's check what the camera sees if I keep the sodium tube cold and just turn the arc on. The sodium tube produces no up and down dispersion because it is cold. The glass prism disperses horizontally. Red at left, light green at right. We see that the sodium prism bends the light down on the red side and up on the green side. Refraction is toward the normal on the red side because on this side the phase speed of light through the vapor is less than c. And refraction is away from the normal on the green side because it is more than c. Notice the qualitative resemblance between this spectrum of the two crossed prisms and the dispersion curve we derived on basis of our classical model. The reason why the spectrum does not reflect the curve continuously is also clear from our model. There is absorption at the resonance. In high dispersion, the yellow sodium light is found to be a doublet, two spectral lines separated by 6 angstroms as to wavelength. So there are really 2 resonances. We see 2 dispersion curves next to each other. Our experiment with the sodium vapor prism proves that, above resonance, the light rays are bent away from the normal. In other words, the experiment proves that the phase velocity can indeed be larger than c at some frequencies. To conclude, we'd also like to tell you that the quantum mechanical theory of dispersion leads to the same result in almost every detail as does the classical explanation we have presented in this film.